Welcome back to another video in our course on probability theory. We are in the topic of conditional expectation, and today we have a special topic which is conditional independence. Of course, you already know about independent random variables, and today we are going to say something similar, which is two things are independent but only given something else. One example, which is maybe generic, is our random success probability. There, we first drew the success probability, which was called U, and afterwards we threw a coin with independent experiments. And that's exactly what conditional independence is. So two of these coin tosses are independent given the U, the joint success probability. So let's see how that translates to things with sigma algebras and stuff. So, conditional independence. Let's first start with a lemma. And, well, there will be versions of this lemma also later in the video. So, when are two sigma algebras independent? Okay, we know when they're independent. That's the case if and only if for all G in G and H in H, we have that the probability that G intersected with H equals the product P of G times P of H. Okay, there's another thing. That's what the lemma claims. That's if and only if the conditional probability of G given H equals the probability of G. Let's try to prove this. And yeah, I'm writing always here G is in G and H is in H. So first of all, from left to right, they're independent, and I have to show this thing here. There is the defining property of the conditional probability here. And of course, P of G is also H measurable, which means if I can show the defining property also for P of G, then I'm done. And the defining property has something to do with the probability of G given some H in H. So I have to show that this here is the same as the expectation of indicator of G given H on the set H. So, because then this here fulfills the defining property of this. And of course, this here is by definition the same as the expectation of the conditional probability of G given H on the set H. So, this is by definition. Yeah, on the other hand, what's also true, so this here apparently is the probability of G intersected with H. And this here is P of G times P of H. And this product here, of course, is this here because that's an expectation of a constant. So I can pull out the constant and I'm left with the expectation of the indicator of H, which is the probability of H. That means I'm done with one direction. The other direction, if the conditional probability of G given H equals P of G, why are then they independent? So I start with the probability of G intersection with H. That's the expectation of the indicator of G along H. By using the definition of the conditional expectation, I can exchange the indicator of G by the conditional probability G given H over H. Then I can use what I have, which is the conditional expectation equals the probability. Then I have the expectation of P of G on the set H. Now again, P of G is a constant which I can pull out of the expectation, and the expectation of the indicator of H equals P of H, and I'm done. Okay, so that means we have a new means to show that two things are independent by saying that a conditional expectation or a conditional probability satisfies something. Now let's slowly move towards conditional expectation, conditional independence. Think of a Markov chain. Maybe you did not have this in your basic course, so let me just say what this example here is about. Draw a coordinate system. Here I have t on the right and xt upwards. In each time step, I have plus or minus 1, which I'm adding or subtracting, like this. And that's the following. So the y's here are 1 with probability p and minus 1 with probability 1 minus p for some pre. And xt sums them all up. So from one step to the next, I have one more of the y's, adding plus or minus 1 to the path. And then what you realize is, for example, when you're at this point here, the probability to go to this xt plus 1 or to this xt plus 1 only depends on where you are here, but it does not depend on where you came from. So this path is irrelevant, but of course the point where you currently at, that's relevant. And that means xt plus 1, so what you do here, is independent of x0 until xt minus 1 given xt. That's how we will call this. Given xt, xt plus 1 is independent of the past x0 up to xt minus 1. And of course, we have a version using random variables and a version using sigma algebras. Sigma of t and sigma of t plus 1, given sigma of xt, sigma of xt plus 1 is independent of the past, given by sigma of x0 up to xt minus 1. Here's a typo. And this here is conditional independence. I mean, what's independence? So there's a product rule, so to speak. On the left-hand side, well, what do I have here? I will call this the probability of the intersection of aj, j, and j given g. And this here should be the same as the product of the probabilities of aj given g, j, and j. So I have here the same product formula as for usual independence. The only difference is that I condition both sides on another sigma algebra G. And then we say, given the sigma algebra, the events aj here are independent. Of course, if that applies to all aj and cj, we say that the cj's here are called independent. And as usual in independence, we do that for all finite subset of our index set I. And that's fine then. Some trivial things. If g equals f, well, g equals f is boring, because if g equals f, I have that the conditional probability that p of a given f, that's the indicator of a. Why is that? Because the indicator of a is, of course, f measurable. And so indicator of a satisfies the defining property of the conditional expectation. We are done. And, well, the indicator of an intersection of AJs is, well, if you want to evaluate this, it's just the product of the indicators of the single ones. So that's trivial. And the other thing is, if I only have the trivial sigma algebra containing the empty set and the full set, then the CI's are independent given J if and only if they're independent. And the reason is, well, the conditioning on J here, that's the same as leaving it away for this kind of condition as we had previously. And then you have the same equation as before, but conditioning on G falls away, so we have regular independence. Let's make an example. What I also mentioned at the beginning, the random success probability. Here I have, as already seen in the previous talks, a random success probability called U, which is uniformly distributed on 0, 1. Let y1 to yn are all independent, but that's not right. This n here must be a 1. So these are single coin tosses, and x is the sum of all these, which is then binomially distributed with n and u. Then consider some interval maybe, or so a measurable subset of 0, 1, and some numbers y1 to yn equal to k. Then I can compute here the expectation of, well, this indicator on the set. And how do I do this? Well, first I have to realize my success probability somewhere in I, and then I have u to the power of k, 1 minus u to the power n minus k. And that's the same as the expectation of u to the power of k, 1 minus u to the power of n minus k. So what we just proved is that the conditional probability of this here, probability of y1 equals y1 up to yn equals yn, equals u to the power of k, 1 minus u to the power n minus k. We also had that previously, I think. Given u, I have to say. And that's important. Why is that? Because the right-hand side here satisfies the defining property of this conditional expectation on the left-hand side, which involves this expectation, which is on the left-hand side on this equation. And for this reason, well, we also have, for example, that the probability of y1 equals 1 given u, that's u. And for this reason, we can write the probability of, well, let's say the intersection j of the sets yj equals yj given u is the same as the product j from 1 to n, probability of yj equals yj given u. So, as said in the intro, the singular coin tosses are independent given the random success probability u. That's what we have here. Okay, there's one more thing that we need. And that's an extension of we had at the beginning. So here we had G and H are independent if and only if something holds. And we also need this for conditional independence. And that looks as follows. G and H are independent, another typo here, given K, if and only if this thing here holds. So if you forget about the K here, so if K is trivial, it's exactly the statement that we had at the beginning. But now we have the K here, and we just have to condition on K everywhere and say G and H are independent given K. Let's try to prove this. at least almost prove this. So let's take G is in G, H is in H, and always K is in K. We have the direction from left to right, so I can use conditional independence, and I have to prove the right-hand side. And I'm going to do this by showing the following. The expectation of the conditional probability of G given K on H intersected with K equals the expectation of the probability of G given sigma of H and K on the same set H intersected with K. So why is that enough? So apparently this conditional probability is measurable with respect to H intersected with K, is measurable with respect to the sigma of H intersected with K. It's measurable with respect to the sigma algebra generated by H and K. Of course, this here also is measurable with respect to sigma algebra K. Therefore, it's also measurable with respect to the sigma algebra generated by sigma of H and K. And if we have shown this here, we have shown that this conditional probability satisfies the defining property of this conditional probability, and therefore they must be the same. Okay. I mean, almost. It's not really the defining property. It would be the defining property if we would have here at the back some arbitrary set in sigma of H and K. But we don't have this, we just intersect them. But we are doing this first, and then afterwards we extend this to more sets which can sit here in the back. Okay, so this expectation. I need something here. I need something from this here. I need this funny property. That means, well, if I have an expectation, and I have an expectation of a product of two, where one is a conditional expectation, I can also shift the conditional expectation to the other variable, and I can also use conditional expectations on both sides. And what I will also need is, like this here, if I have a conditional expectation of a product, and one of them is measurable with respect to the sigma algebra, which is written down here, I can pull it out. Here. So here, that's basically the indicator of H intersected with K. And I use this property in order to write the expectation of P of G given K times the probability of H intersected with K given K. But I'm only having H here given K, and I'm pulling out the K, which is measurable with respect to the sigma algebra K. So like this. I have to now use what I have here on the left-hand side. They're independent given K. And I have here the product. And that means I can translate this to P of G intersected with H given K on the set K. Like this here. But okay, the defining property of the conditional expectation written down here is the same when I leave this out and when I write here indicator of G intersected with H. So I have here the probability that G, H, and K are satisfied. I can also write that down as the expectation of indicator of G on the set H intersected with K. H intersected with K is in the sigma algebra, which is generated by H and K. And therefore this here, the last equality, is the defining property of the conditional expectation, where the condition is on sigma of H and K. Okay, we're almost here, and I will omit something, but I will mention something, that I can now define set D, which is the set A in sigma of H and K, with the property that I can use this A here from the left to the right hand side of the sigma algebra. E P of J given K on the set A equals, well, I'm using this here because the last bit is anyway only a definition, is the same as P of G intersected with A. Okay, and if you can show that this here is the full sigma algebra, then we can do the calculation that we just did for all H in sigma of H and K. And you're doing this by saying this D here is a Dynkin system, which is intersection stable. You have to show this, of course. And then there was a resultant measure theory that if something is a intersection stable Dynkin system, it's not smaller than the sigma algebra. Yeah, it's a sigma algebra, yeah. And at least we have these things here in it. So it's not smaller than sigma algebra generated by H intersected with K. So it's not smaller than H, it's not smaller than K, so it's not smaller than the sigma algebra generated by both of them. So cap-stable Dynkin system, and that's it for the one direction. I mean, you have to do something here, but I won't show you this, but it's in the manuscript. And then let's go also from right to left here. So I can use the right hand side, and I want to show conditional independence. I'm starting with by saying the probability of G intersected with H given K. And I have to end here with a product P of G given K times P of H given K. First of all, it's a probability, so it's an expectation of a product of indicators, like this. Then I can use a condition here. Expectation of, well, I want to condition on the sigma algebras which is generated by H and K, and I'm using this here. But H is measurable with respect to the sigma algebra, only G is not, so the expectation of G conditional on the sigma algebra generated by H and K. Indicator H, conditional on K, like this here. Well, that's the conditional expectation here. That's for the conditional probability, because here's an indicator function. But I have this here, P of G conditional on the full thing is something else. So that's the expectation of the conditional probability of G given K times the indicator function of H conditional on K. Okay, this here probability is measurable with respect to k, so I can pull it out. So that's the p of g given k here. And I'm left with the conditional expectation of indicator of h given k, which is exactly the second part here. Which means I'm done with the back direction, and we have shown that we can extend the first theorem of the video to conditional independence. Okay, and let me just make an example here from Markov chains. Usually that's written as follows. I have, so in this random walk example that we had, for example, xt plus 1 is doing something. That's an event in J. I want to say that they're independent given something. The something is the present. So sigma of xt, that's my k. And the h, that's independent from h, that's the past. That's the sigma algebra generated by x1 until xt minus 1. And conditional independence is, well, I can leave out h, which is exactly the past. So this here is how usually the Markov property is written. So the future, given the whole path up to t, is independent of the past given the present. So that's exactly here. Xt plus 1 is independent of x1 up till xt minus 1 given xt. That's just for this example. And we're done with this video, and next time we are doing some other thing that's interesting from conditional expectation, which is the regular version of the conditional probability. See you then.